Hello and welcome to the second part of the inaugural episode of Datadog On, which is a new series from Datadog. My name is Jeremy. I'm the Director of Technical Community and Open Source here at Datadog. And for those of you who didn't join the first part of this, which was Datadog on Kafka, I'm going to give you just a very brief overview of what the series is, then a little overview of what this specific episode is, and then I'm going to hand it off to Ara for everyone to get started. So in the process of building and monitoring an analytics platform that ingests trillions of data points a day, Datadog has learned many lessons about scaling, about distributed systems, specifically about distributed systems in the cloud, and we would like to share those experiences with you, our community. So each episode, we're going to offer a conversation with the engineers who build Datadog. They'll share real-world experiences about architecting, building, operating, and monitoring modern systems, and importantly, we'll give you actionable information that you can apply at your organization. Now, one core tenet of this series is that we're going to leave plenty of time for QA, so we very much want you to join the discussion. So the session, we've allocated roughly an hour, but like I said, don't be shy, use that Q&A button. We would like you to participate in this very much. So with that, what is this episode? Well, this is Datadog on Kubernetes, where Ara is going to chat with Laurent, who is a staff engineer here at Datadog. And we're going to cover the challenges we found creating and scaling Datadog's Kubernetes platform and how we overcame them. And we're going to cover everything here from scaling the control plane to security, certificates, networking, our open source contributions into the ecosystem, and quite a bit more. So without further ado, I'm going to go ahead and let Ara get started with Datadog on Kubernetes. Once again, don't be shy, jump in with questions. And if you did have folks in your organization that weren't able to join us, we are recording this session and it will be posted shortly. Thanks.
Thanks a lot, Jeremy. Okay, so yeah, Datadog on Kubernetes. So we are going to learn a lot about Kubernetes with Laurent. I think the best thing to get this started is to get Laurent to introduce himself. Laurent, can you introduce yourself?
Sure. So hello, everyone. We're very happy to share with you our adventure with Kubernetes. I'm Laurent Bernaille. I'm staff engineer at Datadog. I've been working at Datadog for 2.5 years, and I'm mostly working on Datadog's Kubernetes infrastructure. I've already gave quite a few talks on the topic, and we're going to share some of the things we found while deploying Kubernetes.
Perfect. So my name is Ara Pulido. I'm a developer advocate at Datadog. I've been working on Kubernetes projects for quite some time now, and it's great that I have the opportunity to talk with Laurent today because I joined Datadog about 10 months ago, and the first thing that I did when I joined Datadog was trying to learn how we were running Kubernetes at this big scale, and Laurent was kind enough to join me in a couple of talks and calls to get me started. So for me, it's a great honor to have him today. So what is Datadog? So obviously this talk itself is not about Datadog, it's about Kubernetes, but just so you know, it's a monitoring and analytics platforms that help companies improve observability of their infrastructure and applications, of course, including Kubernetes as an infrastructure, so Kubernetes itself, the clusters, and the workloads that you run on top of Kubernetes. And I think to understand some of the decisions that Datadog made on their infrastructure, I think it's important to introduce a little bit at what scale we are running. Datadog has more than 8,000 customers, and we get information from the infrastructure of those customers and their applications. So we run the Datadog agent on the customer hosts, gathering all that data back. So we have that data from millions of hosts, and that translates into trillions of data points every single day. So to get Kubernetes to be able to run all of that, we have a big infrastructure. We have thousands of clusters, each cluster, some of them thousands of nodes, and we run on different clouds. So everything here is a little bit complex, and these are the reasons. But before jumping in on how we run Kubernetes, I would like Laurent to explain us what we were using before Kubernetes and why we decided to move to Kubernetes.
So we started the project to migrate to Kubernetes about when I joined, and Before that, we were actually running on VM on AWS, and we're using Chef to manage our instances. This was working fine, but we had a few issues, mostly related to scale and also to immutability. So at that point, we had to choose the next platform for Datadog, and we had many issues we wanted to solve. We wanted to go multi-cloud. We wanted to create new regions, and to address this, we decided to move to Kubernetes. So just to give you an idea of the factors that came into the process. So the first one is, as I was saying before, we were using Chef. And so we were not having the benefits of immutable infrastructure. So moving to containers was a big move for us. Also, as I was saying just previously, we were moving to multi-cloud. And so we wanted to have an abstraction that would make the difference between the clouds as small as possible, so applications could deploy across different cloud providers in an easy way. Also, we knew that the community around Kubernetes was very active at the time, and a lot of components were appearing in the ecosystem and were very helpful, so it was a very good thing. And finally, and that's actually a very important point, we're starting to have customers that were using Kubernetes on their own, and they wanted us to provide the best monitoring possible for their own Kubernetes installations. And we figured that the best way to do that was to actually run Kubernetes. So we would monitor Datadog with Datadog on Kubernetes, and we would be able to learn a lot from it, which we did. And this is why we chose Kubernetes.
Sounds good. Okay, let's start diving in on all the different decisions that we had to make. The first one that we are going to talk about is a control plane and how we run it in a high availability architecture. So just to introduce the topic, the control plane in Kubernetes is a set of processes that basically manage the cluster itself. So those components are the API server. Everything in Kubernetes is an object that you can drive through the API. The controller manager, that it's a process or processes in this case that manage the reconciliation loop in Kubernetes. The scheduler, which basically puts the different workloads on the worker nodes, and etcd to maintain all the states of the cluster. Usually when you put this all together in the same node, you're talking about a control plane node or a master node. Basically in opposition to a worker node, which are the nodes in Kubernetes that actually run your containers and have different processes like the kubelet, container runtime, and QProxy, which QProxy will explain later on what it is. So usually, if you have to run this in production, you have to make sure that if one of your control plane nodes goes down, your cluster continues working. So obviously you need more than one. And when you want to have this HA architecture, this is the first thing that many tutorials offer you. For example, not only tutorials, kubeadm, which is a tool to create Kubernetes clusters. This is the first option that they offer for HA control plane. But this actually has some scaling issues, isn't it, Laurent? Can you talk about those a little bit?
The first thing is, as you can see on this slide, all components seems to be independent, but actually the first one, the one on the bottom, etcd, isn't. All etcd nodes actually need to form a cluster, so data is replicated between the etcd nodes, which is very different from API servers, controllers, and schedulers. And so the first step is usually to actually move etcd out of the cluster, as this slide is showing. The slide shows 5 etcd nodes. So the minimum is usually to have 3. So you have redundancy, and you make sure that if you lose a node, you can still get current from the other 2. However, we decided to go with 5 for all our clusters running critical workloads, just because, as you can imagine, at our scale, we have clusters with a lot of API calls happening every second. And if we lose an etcd node, we need to replace it, and that can take some time. And of course, during the replacement, we could be in a situation where we lose a second node. Of course, if we only had 3, in this situation, we would lose data. That's why we decided to go with 5 nodes. The next challenge is the three components in blue have very different life cycles and very different scalability behaviors. So API servers are almost stateless, which means you can scale them horizontally. So you can add many API servers as you need, and this will help handle the load for the cluster. To give you an example, on very large clusters, we sometimes have up to 9 API servers. However, controller and scheduler are using leader election, and so at any given time, you only have a single active controller and a single active scheduler. So it doesn't really make sense to run 3 of them in this example, or 9 of them if we go back to the architecture I was describing before for our large clusters. So what we ended up doing was scale API servers, controllers, and scheduler independently. So in this example, you have 3 API servers, but as I was saying before, you can have more. However, we're only ever going to have 2 schedulers or 2 controller managers, because as I was saying before, only one is going to be active. So you only need 2 for high availability.
Very interesting. So obviously if we are explaining here how we are running the control plane is because we are running the control plane as opposed to Kubernetes managed services like Jiki or EKS that the control plane is managed by the cloud. Do we know, because this is quite different from what I've seen on the tutorials on how to HA the control plane, do we have any ideas on how the public clouds are running those managed control planes on those services, or it's completely closed source, we have no idea?
So we don't have details on the way it works under the hood, because what you only get when you create a managed cluster is basically an access to the API servers, and you only have access to this API, and of course you have your worker nodes. However, from documentation and from discussions we've had with other people, it's very likely that most cloud providers use master with the 3 components running together. And the main reason for this is they prefer to use vertical scaling a lot. So you use huge nodes to manage the control plane and avoid splitting it, because then it's simpler to manage. And their main challenge is that they have hundreds or thousands of clusters to manage. And of course, the simpler the architecture, the better. On our end, we wanted to optimize things, because we have a lot of clusters, but it's dozens of clusters, not hundreds or thousands. And
this gives a lot of hosts to manage the control plane. So if you have one host for the controller manager, one for, well, in this case, two for the scheduler, X for the API server, depending on how many. I was wondering if those are almost always the same number, why you didn't decide to put the scheduler and control manager in the same host and scale those together?
It's actually a design we looked into at one point. And the main reason we decided not to use this was from experience we had when we were running API servers, controllers, and scheduler on the same nodes, which is the active controller manager has a huge impact on the performance on the host it's running on, because it's very CPU intensive, which means what we observed when all the 3 components were running together was that the controller manager was actually starving the API server for resources. And of course, even if the API servers are out, this could also apply to the scheduler. And as you can see on this design, it's nice because we have one controller manager active on a node, one scheduler active on another node, so it's perfect. But you actually have no control on which one is going to be active. And so you may end up in situations where the behavior is going to be different and the performance are going to be different, depending on whether controller manager and scheduler are running on the same node or on different nodes. So it felt a lot safer to actually use different set of nodes for both components.
Cool. Let's switch gears a little bit to talk about certificates. Certificates are needed to basically secure all the connections between all the components on all the components that are part of the cluster. I know that we're heavily users of Vault to manage all those certificates. We have not only for certificates, but also for secrets. We actually have 3 PKIs in Vault, and the reason why we have 3 is because each of those is to issue certificates for different communication between the components. So You can see here on this graph which components or the connection between those are managing each PKI. But there is this concept. It seems like everything was super tight. Like everything was very well thought. We use Vault very heavily. We're very heavy Vault users. There is this concept sometimes on the 1-year course in Kubernetes where after a year things start to fail. It seems like with everything tight and running in Vault for rotation of those certificates, etc., it seems like we had everything very well tied. Did we get this 1-year course problem as well?
Yes, we did. And as you were saying, I mean, we did everything to avoid it. And the main reason we're using Vault for certificates is it was to make sure that certificates were rotated very often, so we could find issues very early and avoid the 1-year curse, which happens very frequently when you use a normal tutorial where you create, say, some certificates that are valid for a year. So we were completely fine on the control plane and on etcd because we're rotating certificates daily. So we found a lot of issues by doing that, but this was working fine. However, after a year, we still had an issue. And the reason is that the only component where we were not using Vault to rotate certificate was the kubelet. So we were using a feature from Kubernetes called TLS Bootstrap, where kubelet can get their certificate from the Kubernetes API. And the way it worked in our case was the kubelet would get a Bootstrap token from the Kubernetes KB store and supplies its Bootstrap token to the API server to get a certificate signed. And it would get a certificate valid for the cluster. And this was working fine. And at that point, TLS Bootstrap was issuing certificate for a year. So a year later, what happened is, well, we had an issue on the cluster where nodes couldn't join the cluster anymore. And team started complaining that some nodes were taking 20 minutes, then 30 minutes to join the cluster, which was very bad. I mean, usually it takes maybe like a few minutes just for the time for the VM on the cloud provider to boot up. And so this was very weird. So we looked at the log, we couldn't find anything. And we started tracing API calls. And we saw that the last call made by the kubelet was actually a call to get a certificate. And as you saw on the slide before, the shape of the curve was actually increasing a lot, and it was the number of certificates that were pending on the control plane. So certificates that had been submitted for signature and that hadn't been signed. And of course, as you saw, I mean, we had tens of thousands of certificate signing requests not signed, which means the controller responsible for this was taking a very long time. And so new nodes were taking a very long time to join. And what actually happened is, well, we thought that everything was set up right and we were able to get certificate when the nodes were created. However, it turned out that the kubelet is using a different authentication mechanism to renew certificates. So when you create the certificate the first time, you use permission associated with the Bootstrap token. However, when you renew certificate, you use the node certificate to actually ask for renewal, which means creating the certificate was fine, but renewing it was not possible because the kubelet user was not allowed to. And so it was failing to renew. And we were lucky because the kubelet was actually trying to renew the certificate a long time before it was actually too old, which means we had the chance to catch the issue before it actually became a very bad one.
Cool. And what did we did? We just fixed the RBAC issue, or did we change completely how we were managing the kubelet certificates?
So the first thing we did when we had the incident was to delete all pending CSRs, fix the RBAC issue, and everything went back to normal. However, we were a bit terrified that we had other small issues in there. And so we decided to move kubelet certificate management to Vault 2. So now all our kubelets are getting the certificate from Vault, and these certificates are also rotated daily. Hopefully
not more problems in a year time.
Hopefully.
Let's talk about networking now. And Kubernetes networking I think could be topic for a series itself. It's quite complex. So we are going to try to divide the topic into several sections. We will start talking about pod networking, and basically pod networking in Kubernetes. A pod is basically the minimal deployable unit in Kubernetes, which is one or more containers that share the same networking namespace. And pod networking is a set. Well, let's say it's a set of rules that the cluster has to match, that basically says that every pod is going to get a unique IP on the cluster, and that every pod can route traffic to any other pod. So you should be able to route traffic between any pods in the cluster. There are several ways to do this, because actually Kubernetes is not doing this by itself. It doesn't have a canonical implementation, so you have to implement this yourself. And there are several ways. The simplest way would be to create those routes manually, which obviously is not ideal, because every time that you add a node, remove a node, you have to change those routes. So most people, what they use, it's our CNI plugin. CNI is, or Container Network Interface, is a specification by the CNCF, which basically is a spec that says, if you want to implement pod networking, this is how you have to do it. Or even if you want to collaborate, let's say, with another plugin, so if you want to take features from one or the other, how to do that as well, because you can mix and match. So because it's a spec that basically opens the implementation to anyone, there are a lot of implementations of pod networking and CNI, and each of those work very, very differently. The most basic one, and one that usually people start with, is network overlays like Flannel. Actually, if you run a very small, one of these simple distributions of Kubernetes like Micro Kubernetes or K3s, they're using Flannel, because it's very simple to understand. Basically what it does, it's create an overlay, a network overlay for, and all the pods are going to get an IP from that overlay. And when you want to route traffic between pods that are on different nodes, what it's going to do, it's going to create this interface called Flannel on every node. And basically Flannel is going to maintain an etcd table, with subnets and different nodes. So it knows every subnet where it goes, and it's going to create an IP on IP. So it's going to create a new header for the packet, and it's going to route to the next hop, to the next node. When it arrives to the node where the pod is, it's going to do the opposite. It's going to remove the extra header, and it's going to reroute the original packet. And so it's very simple to understand and very simple to debug, but it has some scaling issues, isn't it, Laurent?
Yes, I mean, the main challenge of overlays is you have to distribute routes to every node, because every node needs to know where each CIDR is located. So to create the route you were just mentioning, you need to know that the CIDR given to a node is actually on a node with a given IP. And doing that at scale is very difficult and creates a lot of load on the backend you're using, which, depending on the solution you use for overlay, can be etcd or BGP, for instance. In addition, overlays have a cost. I mean, you were mentioning the additional header to route packet between nodes. And of course, this has a cost both in terms of packet size, but also in terms of CPU, because your Linux machine will have to compute all this, and this will require a lot of extra cycles. And of course, this has a performance impact.
So what's the alternative when you're running at a bigger scale?
So we knew from the start that that using an overlay was going to be challenging for us, because a lot of our applications are very network intensive. They process a lot of packets at a very high throughput. And so we needed the network to be as efficient as possible. And also, we knew that we would have clusters with thousands of nodes. And we're pretty lucky, because at the time we started working on Kubernetes, people were starting to move out of overlays, which were the first solution implemented. And the reason it was the first solution implemented is because overlays actually make the underlying network completely transparent, and they will work wherever you are, which is very convenient. However, people were starting to see the performance issues I was just mentioning, and most cloud providers and most providers were starting to move to native routing. And by native routing, I mean giving pod IPs that are routable on the network. So on AWS, for instance, AWS is providing a plugin for EKS and also created a plugin doing exactly the same. And we've been using this one for quite some time. And I'm just going to show you how it works. So basically your CNI binary is going, when it's called by the kubelet to create a network namespace and allocate an IP to a pod, it's going to call a daemon that is going to be responsible for managing networking. And this daemon on AWS is going to attach an additional network interface if needed and allocate IPs on this interface and give this IP to the pods, which means in the end, pods get an IP that is an IP of the VPC. And so we're using the software-defined network from AWS, and we're not adding another one on top of it.
You said that when you were starting, people were already moving, especially when at bigger scale, moving away from overlay. So this was basically our first solution. Did we start with direct port routing? We were using something else.
Yes, we started with this, exactly. And we evaluated multiple plugins doing this, and we decided to use Lyft, which was the best one according to our needs at the time.
Okay, so the next part of networking that we are going to be talking about is service networking. And service networking basically in Kubernetes is when you have a service, a workload, a service in Kubernetes. For example, you have a front end and a back end service that are part of your application. Your front end pods are not going to be talking directly to the back end pods. Basically, the pods are ephemeral. They can come and go. They can be destroyed. They can become unavailable, etc. So there is this concept in Kubernetes called a Kubernetes service, which basically is going to load balance traffic between the different pods that are part of the same service. And this is actually implemented by Kubernetes itself through a component called QProxy. And QProxy has two modes of working. And the default one, and because it's the default one, is the most used, especially when people start, it's using IP tables. And the way it works is that QProxy is one of these components that we were mentioning at the beginning that are part of the worker nodes. It's going to be on every single of these worker nodes. And it's going to be watching all the time the API, the Kubernetes API for pods that get created, pod that gets destroyed, services that get created or destroyed, pods that are not, that are failing the readiness probe, and therefore they cannot get traffic, etc. And with all that information, it's going to be updating the IP tables, not table of the specific node that it is. So when a pod in that particular node needs to talk to a service, it will start matching some rules on the IP tables not table, and will basically randomize which pod of that service is going to pick for that traffic. But this, again, has some issues. Even though it's the default mode still in Kubernetes, it still have some scaling issues.
Yes, I mean, the main challenge is as soon as you have a large number of services and endpoints backing the services, the size of your IP table rules is going to be very impressive. And for instance, I remember at one point we had a cluster with about 1,000 nodes, which is quite a big cluster, but we knew we needed more. And for a cluster of this size in our specific deployment, we already had tens of thousands of IP table rules, which is quite a lot. And the biggest challenge is every time there is a change in endpoints, the way it works is the full IP table chains are going to be recomputed and reloaded, which takes a lot of time. And so, yes, IP table was very limited. And so we decided to move to another solution. And yes, the example on this slide is actually an issue that's still open. and is exactly illustrating what I was saying, which is, well, if you have a lot of services, what's going to happen is, well, it's going to take a long time to reload the QProxy, the IP tables rules, which means it's going to time out because the default timeout is 5 seconds. And that entails that it's going to take more than 5 seconds to reflect any update in the cluster, which is a very long time, of course. Now, when we started, we knew IP table was going to be challenging. And we also knew that a team at Huawei had started on implementing another backend for QProxy, and that was using ipvs instead of IP tables. And the main advantage of ipvs is it's actually designed to do load balancing, and so it makes a lot of sense to use ipvs for load balancing. It's been GA in Kubernetes since 1.11, and we've been using it ever since. The main advantage compared to IP tables is anytime there is a change in the list of backends for a service, you only need to simply update this information in the ipvs configuration. And so if you look at the bottom there, if we add another backend for this service, it would just mean that we would just need to make a call to the ipvs interface just to add another IP to the list of backends. And that's very fast and very efficient. And yeah, that was the main advantage. And in terms of how it works, the design is exactly the same. It's the same QProxy, you just change the way it's configured by enabling ipvs. And it looks the same, except that load balancing is now done by ipvs.
So ipvs, I saw that it was GA on Kubernetes 1.11, which is already quite old. But even though it was GA on 1.11, I can see that there was some issues that actually you needed to solve.
Yes, I mean, ipvs was GA in 1.11. However, it was not providing graceful termination. And which means when you were removing an endpoint, it was removed immediately without giving the application the chance to finish what it was doing. And that meant that for web applications, for instance, you would start your connection and you wouldn't be able to get your data back, which is not great. And IP tables was supporting this natively from the start. And so there was an implementation doing graceful termination, but it was very new. And it started in the release cycle of 1.11 in the middle of it. I think it was 1.11.5 or something. And we had quite a few issues with it because it was very new.
Yeah, I can see that actually you contributed quite a lot to ipvs, and I think you became a maintainer at some point.
Yes, I mean, we were using it a lot, and we were finding small bugs and small improvements, and so I started creating issues, and then I started to provide small and simple pull requests, and after some time, I got to know the code base pretty well, and yes, I ended up a maintainer of the ipvs code base of QProxy.
So what would be your recommendation for people who are willing to start contributing back to Kubernetes?
The community is very welcoming. It was very easy for me to get involved. To get started, the best is probably to find a component you use on which you rely on heavily and that you start to know well. And when you find an issue, you just create an issue and then you start interacting with maintainers. And as you understand better how it works, you start providing pull requests and so on. And you build a relationship and you get to be a maintainer or at least a contributor to a specific part of the code base you know well.
So the last part that we are going to be talking about networking, well, we are going to be talking afterwards about DNS, but on this section is Cilium. So I've seen that you invested quite a, well, as in the team invested quite a bit of time with Lyft, for example, for the plugin, with ipvs, but now you're starting moving to something else called Cilium. What is a Cilium exactly?
Cilium is a tool, an open source tool that was designed to do container isolation and network traffic policies. And it was designed to do this very efficiently using eBPF, which is a very efficient way to load custom code in the kernel. And as they were working on security, they figured that they could also do service load balancing in eBPF because, of course, they were already modifying traffic or dropping traffic. And so they did that. And then they realized that it made complete sense, and they were managing the interface to pods to actually control the CNI part of it also. And so we are actually now moving to Cilium, which is responsible for CNI. So Cilium is creating all the network namespaces and giving pod IPs. And in our case, it's doing this by using exactly the same thing I was mentioning before, which is give pods IP that are runnable on the VPC. And it has a nice advantage in terms of design, which is centralized IP allocation. In the case of the Lyft CNI plugin or the AWS CNI plugin, in this application, what they do is every host is responsible for attaching DNI and attaching IP, which creates issues in terms of security because, of course, it means you need to give them permission to do that. And also, it's very difficult to manage rate limits because everything is completely distributed. So it's very hard to manage this efficiently. And having a centralized controller to do that is very efficient. It's also much better for service networking as a QProxy replacement because it's done in eBPF, so it's faster. And also because it was designed from the get-go to be a client load balancer, which neither IP tables or ipvs were designed for. And of course, it also comes with other very interesting features, such as network policies, and also encryption between hosts if you need it. So that's great. And we've had a very good relationship with the Cilium team that's been very helpful to us. And we're using it right now on every new cluster we create.
Finally, DNS. Big topic when we're talking about Kubernetes. So basically, DNS in Kubernetes is there is a component called core DNS that basically gets translate a name service into an IP of the service. But as people were scaling their Kubernetes clusters, people were having some issues with DNS, isn't it?
Yes. The main challenge when you do DNS in Kubernetes is actually the fact that DNS traffic is usually UDP, which means your pods would do a DNS query using UDP, and QProxy using IPVS or IP table would load balance this UDP query to a DNS pod. So this works mostly fine as long as you don't have that many queries, but it creates a lot of issues. And this one is the one that the one on the slide here is one of the issue that was very, very bad for people because it was very surprising and very weird, which is sometimes DNS queries were timing out after 5 seconds. And the reason this was happening was actually a kernel bug in the contract. And so usually what happens is a pod that wants to do a DNS query is going to do an IPv4 and IPv6 query at the same time. And the kernel will have to create 2 entries in the contract, the connection tracking system of the kernel. And there's a race condition, which means sometimes one of these packets is going to be dropped, which means the querier is not going to get its answer. And so it's going to wait for the answer and time out after 5 seconds, which is the default. Another issue with UDP is a very classic one. Doing connection tracking with UDP is very difficult. So you can end up with the contract being completely full and dropping packets again. And of course, another challenge is as your clusters get bigger, the amount of queries you do per second is very impressive. And in our case, for instance, we do tens of thousands of queries per second. So you need DNS to be very robust. And so we decided to improve on the normal typical design.
So that improvement, I think, involves an idea called local DNS cache. Can you explain a little bit what it is and how Datadog implemented it?
So we were not the only one facing the issues I was describing before. Many people were facing them and many people were looking into solutions. And the solution people came up with was to use a local DNS cache on every node. And the main advantage of having a cache would be like, for instance, you won't do UDP traffic to outside the host, so you won't have to do that. You would just do a UDP connection to the node local cache. which would then do a TCP connection to the DNS service and DNS pods. And what you could do too, and what non-local DNS does, is disable connection tracking for this traffic, which means you don't risk the contract being full. That was great. So we decided to go with the same design with some small adjustments. The first one is, since we didn't want to disrupt things for users, we decided to make it opt-in. So people would just add annotations on their pods, and we have a controller that would modify the DNS server based on this annotation to use a non-local cache instead of the cluster service. Which means, of course, that if your pod didn't have the annotation, it would use the standard query. Another improvement we made was to the search path used by the kubelets and we use by pods. So in this slide, you can see the typical resolve.conf you get in Kubernetes. So of course the servers are missing, but you have the search domain and the options. And what's important is to make things simple in the cluster, you have a lot of different search domains. So the first one will include the namespace, then you have only service cluster.local, then just cluster.local, and finally the one provided by your cloud provider. And what's very important here is because you have this very complex domain with a lot of dots, is if you want to make sure that completion will happen in every case, you need to have end dots be equal to 5. The end dot option is controlling the number of dots you need to have in a DNS name for the resolver to consider that it's a fully qualified name and not attempt to add such domains. But of course, since n dots is equal to 5, that means that if you do a normal query such as www.google.com, it has only 2 dots, which means your resolver is going to iterate over all the domains and then finally try and resolve www.google.com. So for a single query, you're actually doing 5 queries. And if you're also doing IPv6, which is very likely because it's the default in most installations, you're going to do 10 queries for a single answer you need. And the optimization we made was, we decided to make the search domain much simpler at the cost of making things slightly more complicated for applications. So as you can see here, we have a single search domain, which is service.cluster.local. And this means that, of course, if you want to address an application that's also in your namespace, you need to put the namespace because this will not be expanded. So if your application is trying to reach a service in the same namespace only by name, it won't be reachable because you need to add the namespace. However, it gives us a very nice property, which is now we can go back to n.equal2, which means in that case, you're going to do a single query most of the time. So it's much more efficient. Another very nice thing about this design, the non-local design, is we can also decrease the amount of queries we do by forwarding based on the target domain. So if the domain you're targeting is inside the cluster, the non-local DNS is actually going to forward traffic to the central DNS deployment, which we were talking about before. But if it's not, the query is going to be sent directly to the cloud provider DNS. And this means less queries going to the DNS service you manage, and it's a lot easier to scale and it's safer.
That was great to learn all of this with you today, Laurent. Thanks a lot. So to do some final remarks before we move to the Q&A, we have some questions waiting there. Any recommendations for teams who want to migrate to Kubernetes today?
Well, the first thing is, I'd say don't manage Kubernetes yourself unless you have to for very good reasons, because it's hard and you'll need a team that's very involved to do that. So make sure you actually really need it. Managed services are getting better and better on all cloud providers. And I think for small to mid-sized deployments, like hundreds of nodes, they make complete sense. And it's a lot easier and you can focus on your application and not focus on control plane issues.
I'm going to start asking you questions that came from the audience. So the first one that I want to ask you is actually came from the form to register. It was, if you could go back, would you choose Kubernetes again?
So it's clearly been an adventure. It's been hard. We've had very weird and interesting problems along the way. However, I think it helped us a lot. We were using a single cloud before. We're now running on 2 different clouds. We're creating additional regions much more easily, and even thinking about other cloud providers. So this has been very helpful. And also, as I was saying initially, it made the integrations with Kubernetes a lot better because we provided feedback and worked very closely with the teams responsible for monitoring Kubernetes at Datadog.
Another question on the Q&A. How is your cluster lifecycle managed?
The commitment we make to users is when we create a cluster, it's going to be available for a year. And then it's very likely that they will have to migrate to new clusters. So we haven't enforced it strongly yet, but we plan to have teams migrate out of our old clusters pretty soon, probably this year. So this means the lifespan of the cluster, of the oldest cluster, would have been 1.5 years or something, which is a bit long, but I think it's acceptable to give team to avoid having teams move from cluster to cluster all the time. Of course, depending on the teams, for some teams it's very easy, especially if you have stateless services. The challenge starts when you have application with state and a lot of states, because then moving this application to another cluster is more involved.
That has to be scary. We were just, the previous session was about Kafka and how to run Kafka in Kubernetes, so not easy either. So the next question is, do you have a use case for long-lived connections? And if the answer is yes, how is load balancing for those done? So
I'm not completely sure, but I'd say most of our long-lived connections use gRPC. And when we use gRPC, we use direct pod-to-pod connections, which means we don't use a service. We don't use QProxy. So what usually happens is application will create a headless services. So this is a Kubernetes service without a virtual IP. And when you do a DNS query to get the IP for the service, you actually get the IP of all the backends for the service. And then your application is responsible for doing the connection. And I think it's probably the only case where we have long connections, but I may be mistaken.
Now, question, Jacob is asking, how long did your kube migration take?
It's not completely over. So to give you an idea, we had our first cluster ready for production in 6 months, and we actually opened it for completely for users with complete support after, I'd say, 8 months. And now we're in the process of migrating everything over to Kubernetes. And the only reason it's not completely done yet is because we have a lot of other expansion projects in other regional cloud providers, which means in terms of team focus, it's been taking a lot of time from teams. However, we know that we can run a complete version of the platform in Kubernetes because we do in the second cloud provider I was mentioning.
So we know that we can do it. Good. This one is very interesting. Which metrics were key to your etcd and API server capacity planning?
Yeah, so we've been learning a lot on this topic and from experience, because we've had a lot of small issues with these components. From our experience, I'd say the most important is to start monitoring the simplest things, such as memory usage, CPU usage, but also network throughput. And I think the most important one for etcd is probably disk I/O latency and number of disk I/Os, because depending on the disk type you use, you can have issues if your disk are too slow. So be very careful with the disk you use and how you monitor the disk for etcd. If you want to go higher up the stack for both components, you should look at queues and slow queries. So both etcd and API server provide information in terms of how many slow queries did I get recently? And if this starts increasing, it usually means that you have performance degradation, which means you need to be very careful about your control plane. And in terms of queue, most controllers and schedulers will give you the size of the queue they're currently processing. And of course, when this increases, it means that your cluster is getting slower. So it's important to look at this.
There is another question on how do we manage Datadog monitors for all these clusters? And I think this, instead of, it's a good question to ask, because we probably will do a different session on Datadog on monitoring best practices for Kubernetes. And probably all those questions will be answered on that one. The next question that I have is so basically you mentioned that your recommendation would be to use a managed Kubernetes service if possible, but if you need to run on several clouds, like in your case, even if it's in a smaller scale, it's easier to manage everything yourself, or is it easier to manage the difference between the managed services on the different clouds?
So this one is a hard one, and it will be difficult for me to give you a precise answer, because I don't know the managed service well enough to know exactly where they are right now. The main challenge would be the difference in Kubernetes versions, for instance, in the different cloud providers, because of course, you want your applications to use the same version of Kubernetes on all the cloud providers. But if you can do that, it's probably best to do it this way, because you will already have to make sure that you understand the specificities of all cloud providers in any case. And it's better if you do it on a managed service, because it means you will have less things to think about.
Okay, another question about lifecycle. So we've been talking about having a year before they move to a new cluster. But what about upgrades within the same cluster? How often do you do upgrades of?
Very good question again. So we don't do any minor updates. We only do patch updates, which is one of the reasons we support clusters for a year, because after a year, you don't get patches for versions that are older. So yes, I mean, we decided from the start not to do minor upgrades, because at that time it was very scary and it was not well supported and people had many issues with it. I think now it's something we could actually look into, just because it's actually possible that it's much more stable. So that would be interesting. The main challenge will actually be the update of the kubelets, because as I was not saying before, but I could have said before, our nodes are immutable, which means updating the kubelet on these nodes means rotating the nodes, which can be challenging for applications having local data. So it's something that can be done, but it would be very long to do it in a cluster with thousands of nodes.
Question about CNI plugins. So the question is Calico also an overlay network type of plugin? And if yes, then how does it work with GCP managed cluster? And did you try Calico? So all of that is the same question. Someone definitely very interested in Calico.
So this one it's a difficult question, because Calico has many modes of operation. So I'm afraid of saying mistakes, because I'm really not an expert. I think in most cases, Calico will use an overlay to do communication between nodes when you're running on a cloud provider. If you're running on premise, you can run Calico in routing mode, in which case you're just going to use routes on the node to target the other ones. However, I think on cloud providers, I'm sure on AWS that if you want to have traffic between AZs, you need to do encapsulation. And I think in the case of Calico, it's IP in IP. In GCP, I'm less sure. The main challenge with Calico at scale is actually route distribution, which is another challenge I was mentioning before, because you need to distribute routing information and CIDR information to all nodes. And the way you do that usually, and once again, it may be different in recent version and there might be other options, is to use BGP. And when you start reaching hundreds of nodes, you can't have a full BGP mesh between all the nodes to distribute this information. And so you need to start entering complex BGP architecture, usually using route reflectors, for instance. And you need people that are able to manage it and to operate it. The main advantage of using solutions from the cloud provider that will give you IPs on the virtual network directly is that it's more efficient and it's also simpler to manage. And I know that we've been doing that on I know it's possible on GCP to have native IPs given to the pods without Calico.
Cool. Another question: did you do any scheduling changes while running your own cluster? I guess they mean changing how the scheduler works.
We don't. It's something where we've been thinking about. We've thought about it a few times, but so far we're not doing that.
Yeah, simple answer, no. How did you diagnose QProxy and IP tables mode as a bottleneck?
It's mainly the main way to measure it is to measure the latency of rule updates, and you actually have metrics in QProxy that will give you the time it takes to update rules. So this is if you want to have very precise measures. However, if you want to feel it, you can, on a large cluster, you can just delete the pod and see how fast this reflects into any given node on the cluster. And it's going to be some time.
Okay, cool. That was the last question. So I think we can wrap it up.
Yeah, it looks like that's a wrap. Once again, thank you for attending Datadog on Kubernetes. If you have any other questions or there are topics you'd like to see in a future Datadog on, do let us know. And you can stay tuned for the next topic. And like I said, this is going to be a monthly series. So we'll see you in June. Thanks.